Hello everyone, and welcome to today's chem lesson. Today, we are going to talk about covalent bonds and how those form and what makes them different from ionic bonds, which is what we've been looking at for the last couple of videos. In a covalent bond, two or more nonmetals share electrons between them, which is different from what we've seen with ionic bonding, where it's a metal and a nonmetal, and there's a transfer of electrons. Here, covalent bonding is all about sharing, very much like your kindergarten classes. Right? When we look at a covalent bond, we're talking about two atoms sharing electrons between them. In these situations, we have electronegativity differences that are small, electronegativity differences that are less than 2, meaning that one atom is not that much stronger than the other. A lot of our common chemicals, things like water, methane, ammonia, carbon dioxide, oxygen, there's a lot of different things that are all covalently bonded. And just like before, when two elements come together to make a covalent compound, there is a new set of properties that comes with that. The properties of the compound are going to be different than the properties of each individual element. Some of the patterns that we see when we have covalent compounds, not 100% of the time, but most of the time, many covalent substances have these properties, where they are soft, with low melting points, low boiling points, and they are bad conductors of heat and electricity. And if you're noticing, that is the exact opposite of the properties that we saw for ionic compounds. The difference between sharing electrons and transferring electrons is humongous. There's such a big difference between them that these end up being almost exactly the opposite of what transferring electrons did. Right? Sharing electrons gives you almost the exact opposite connections and properties. Also similar to what we did for ionic compounds, we are going to look at how the drawing of a covalent compound is different than the drawing of the regular elements. We are going to spend a ton of time on the drawings for covalent compounds, because that's where a lot of our information is going to be. Almost all of the information that we need is going to come from the drawings and the dot structures of our covalent compounds. Now, when we look at covalent drawings, we are still looking at Lewis dot diagrams. We're still looking at putting our valence electrons around the symbol of the element, but we're not looking about transferring. We're not looking to transfer those electrons from one thing to another. We're looking to share them, and that's going to look a little bit different. We're going to basically overlap two elements like a puzzle piece, where these electrons that they have are going to help satisfy the missing parts for each other. We're basically doing a jigsaw puzzle here. And our steps are pretty straightforward. You're just going to draw the Lewis dot structures of each individual thing. Right? There's N and 3 H's. And then you're going to find how these elements click together. How do they fit together like a puzzle to make each one look like a noble gas, to fill the valence shell? Which means almost everything gets 8. Hydrogen is the only exception. Hydrogen wants 2. And here, when we look at these examples, we're going to ask ourselves, or repeat to ourselves, a very important statement here, which is, every lonely electron wants a buddy. that is what we are trying to do here. We are trying to buddy up every lonely electron. And when we look at our Lewis dot diagrams, for example, let's change up some colors now and look at a purple nitrogen and some red hydrogens. We want every lonely electron to get a buddy, which means these 3 and these 3 for a total of 6 lonely electrons that we want to pair off. Now there are some rules to this. If I'm giving you 4 elements here, they all must connect to each other. I can't just pair off these 2 H's and then connect, you know, the H to the N. It has to be one thing at the end. So I can't make this, because this is just H2 by itself. Everything needs to connect together. And the other big important thing is I can't connect something to itself. I can't connect this purple dot to this other purple dot. I have to connect these electrons to other elements. And the other thing, which is new for us, is the fact that you are allowed to take our template and rotate it. All right, let's put a letter in here, right? Let's say carbon. I am allowed to rotate my dot diagram, my template. I'm allowed to turn it around the symbol. 90, 180, 270, even at a 45-degree angle. I'm allowed to make this rotation so that it's still something that I can read as I look at finished pictures, right? I don't want to have to turn my entire, you know, textbook around to make sense of the letters that are there. They should just be read normally. And so let's take a look. Let's take a look at NH3 and see what we can do with NH3. I know that every lonely electron wants a buddy. And I know that everything needs to connect into one thing at the end, right? I can't, like I said, connect those 2 H's together, because then there's no way those 2 H's can connect to everything else. So that means that each of these H's has to connect back to the N. And I'm going to make these connections. And when I tidy that up, when I clean that up, I'm going to end up with a picture that looks like this, with the H's clicking into place in the missing slots that the N had, pairing up our lonely electrons. And then if I look at what electrons belong to which element, we'll see there's some overlap here. Each hydrogen has 2 electrons, which is what they want to fill their first shell. So that means that these hydrogens are all stable. The nitrogen has the 2 electrons that it started with that were paired, and then another 2 4, 6 for a total of 8 electrons, which makes it stable as well. Through sharing electrons, each one of these 4 atoms has become stable. Now, when we see this drawn in a diagram or a textbook or in a research paper, you will see dashes like this that connect our elements together, which is exactly the same concept as these lines, exactly the same concepts as these pairs of electrons here. Each one of these lines is a bond. And the bond represents one atom from each of the two, or one electron, sorry, from each of the 2 atoms. So this, I'm going to make it green. This green line here represents 1 electron from the N and 1 electron from the H. Exactly what we see here, and exactly what we see here. Each covalent bond is 2 electrons, 1 from each connected atom. Let's take a look at HCl. Oh, I'm going to leave H's as red, actually. I'm going to make this Cl blue. Cl, chlorine, has 7 valence electrons, and so they fill in, just like that. And our H, we're going to go back to red. And our task here, every lonely electron wants a buddy. Here in this situation, there's only one set of lonely electrons. There's only one connection that we can make, so it'll be the H to the Cl there. And when we carry on and draw we can draw them linked like this. We can draw them clicked together like this. Right? No matter how you want to draw it, this is not the final drawing. Our final drawing is going to be this one on the bottom here. And the question in the chat now reads, is every element in a covalent bond complementary? Yes, right? So nitrogen needs 3 electrons, and so it will bond with 3 hydrogens, 3 things that need 1 electron each. Chlorine needs 1 electron, so it will bond with 1 hydrogen. I did pick hydrogen specifically for all of these examples because it is the easiest thing to see. Right? It's very easy to see where hydrogen kind of clicks in to complete a shell. But yes, the idea behind covalent bonding is that these elements, these 2 hydrogens and 1 oxygen, can interact in a way that makes both of them, or all 3 of them in this case, right, 2 H's and 1 O, makes all 3 of them stable. NH3 is 3 hydrogens and 1 nitrogen because that is the combination that makes all 4 of them stable. You would never have NH2, for example, right? If we took one of these H's away, right, let's run that through. If I take one of these H's away, all of a sudden I'm left with an unpaired lonely electron, and we do not want that. We cannot have lonely electrons just kind of hanging out. Right, so when we move on to the more complicated ones, after we take a look at the last 2 here, we're going to see it's always about being complementary. It's always about making all present atoms stable. For H2O, for water, we're going to see 2 H's. Let's go back to blue here for our O with 6 valence electrons. Again, right, as we start to realize what we're looking for, these patterns emerge and make it a little easier to see how we're going to connect these pieces together. We're going to get an H in each of these spots, every lonely electron getting a buddy. The only things that are not connected are things that were already paired off to begin with. Cleaning up our picture is going to show either clicking together, like we've seen here and here, or connected by these lines. Right? Either or is fine for trying to make your picture work. And our final drawing down here in monotone black is O and H connected by these bonds, showing the 2 electrons, one from the O, one from the H, to make the bond. And now we see that shape is actually consistent here. Right, the O was missing a slot on the left and a slot on the bottom, and so those are the 2 places we are going to put our hydrogens. If we ended up with this picture, which still shows pretty much the exact same thing, this picture is incorrect. This picture is very, very wrong, because it does not follow our template here. It does not follow our Lewis dot diagram template. We are allowed to rotate and turn this template around, but we are never allowed to just rearrange and reorganize those numbers. Those numbers are in this order on purpose. The first 2 on top, the 3rd, 4th, 5th, 6, 7, 8, alternating their way around. This picture is incorrect. Water does not actually take this shape. Water takes this shape. If we looked at a molecule of water, this is what it would look like. Now let's take a look at carbon. All right, we've got 4 H's in this one. And carbon. Now carbon is special. Carbon has 4 valence electrons, and those 4 valence electrons, if we followed our template, go 1, 2, 3, 4. But carbon is a very important, very special element because it's actually going to shift these electrons around, but only when it bonds. When carbon forms bonds, these electrons move and rearrange so that there's 1 on each side, allowing for carbon to have 4 bonds to itself, or to other things. 4 bonds total. 1 on the top, 1 on the bottom, 1 on the left, 1 on the right. Right, this makes carbon really special. This is why it's carbon-based life. Right, this ability to make 4 bonds and all the possibilities that that opens up for, different chemicals is what makes carbon so essential. When I make these connections, I'm going to connect 1 H to each side of the carbon for a final picture and a final drawing that looks something like this, with a carbon in the middle and an H on each side. Now let's take a look, just to be safe, at this, right? When these hydrogens click into place, we still get every single atom stable. All 5 of these are stable. Each hydrogen has 2 valence electrons, which is what they want. And the carbon, if I can carefully draw the circle, has 8 valence electrons, 2 on each side. So still, everything is stable here. Let's take a look at some that aren't quite as straightforward as things bonded to H's. All right, let's look at some more complicated ideas. Our base is still true, right? Our baseline mantra here of every lonely electron wants a buddy. That still holds true. That's still our main goal, is to connect all the lonely electrons together. Our Lewis dot diagram template still holds true. All right, we can rotate it around and move them as we need to, but we can't rearrange them. And so let's take a look. Let's go red and blue for 2 oxygens, right? 1 oxygen here, 6 valence electrons. Another oxygen in blue, 6 valence electrons. I am still looking for every lonely electron to get a buddy. And so in this case, I only have one possibility. I must connect these oxygens to each other repeatedly. This is called a double bond for pretty obvious reasons, right? I'm bonding the same thing, the same 2 atoms together twice. They're sharing a total of 4 electrons between them. If I clean this up and try to do our drawing, our final picture here, let's see. This rotates. We're going to move it 45 degrees clockwise to end up with an O that looks like this. We're going to rotate this one 45 degrees counterclockwise. Or more than 45 degrees. 135 degrees. And connect these 2. We're going to end up with a double bond. And when we draw that out the way we will see it in textbooks and diagrams and research papers, it's going to look like this. With those paired electrons in the same place they are in our picture. Right, this angle staying consistent because this is the angle that they're connecting at. And these 2 lines to show the double bond. We've got 1, 2, 3, 4, 5, 6, 7, 8, because each line is 2 electrons, 1 from each oxygen. So left oxygen has 8. The right oxygen is its exact mirror image, so 1, 2, 3, 4, 5, 6, 7, 8. Both oxygens have 8 valence electrons. Both oxygens are stable. So double bonds are totally possible. Let's look at a pair of nitrogens. When I draw 2 nitrogens, each one has 5 valence electrons. I still need every lonely electron to get a buddy. And so in this situation, I'm actually going to make a triple bond. I'm going to bond the nitrogen to the other one once, twice, 3 times in order for every lonely electron to get its buddy. Now cleaning it up, we're going to do a 90-degree rotation. Clockwise for the blue, counterclockwise for the red. Our red is going to look like this. Our blue is going to look like this. 1, 2, 3, 4, 5. And our connections are going to go top, middle, bottom. Cleaning that up for the final official picture, we're going to have a triple bond between our nitrogens. Each bond representing 2 valence electrons being shared, 1 from each nitrogen. Left nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, while right nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Both are satisfied with their 8 valence electrons in their full shells. For carbon dioxide, we get an interesting phenomenon occurring. Right, I'm going to draw out both O's, one red, one blue. Here again, every lonely electron wants a buddy. When we go to connect all these dots together, we're actually going to need 2 double bonds. If we connect the oxygens to each other even once, there is now no way for every lonely electron to get a buddy without the carbon connecting to itself, and that can't happen. So the only way this clicks together is if the carbon makes 2 bonds to oxygen, and then another 2 bonds to oxygen. When we go to draw this in a little bit nicer way, I'm going to make a 45-degree rotation on the carbon. A 45-degree rotation on this oxygen. And that 135-degree rotation on the other oxygen. So that everything lines up like this. For single bond, double bond between red and green, single bond, double bond between green and blue. Every lonely electron has been paired up, and our final picture is this beautiful carbon dioxide molecule that looks just like this. And we can do our baby blue double checking here. 1, 2, 3, 4, 5, 6, 7, 8 for left oxygen. 1, 2, 3, 4, 5, 6, 7, 8 for our carbon. 1, 2, 3, 4, 5, 6, 7, 8 for our right oxygen. Each one stable, each one happy. our last one is CH2O. Let's see. Can you connect together all the lonely electrons in CH2O? Can you find the right bond setup for this molecule? I'm going to put about 1.5 minutes on the clock here for you to try to find those connections, and then we'll look at it together. Our correctly connected lonely electrons in this situation looks like this. The carbon will double bond to the oxygen and single bond to each hydrogen. There is no other configuration that allows all lonely electrons to be paired up. If you connect one of the hydrogens to the oxygen, then all of a sudden there's a leftover set of dots on the carbon, and you can't connect carbon to itself. When we go to clean this picture up, when we go to tidy it up, we are going to have a picture that looks like this. Our oxygen and our two hydrogens kind of making this Y shape. Connecting together to give us a final picture that looks like this. And when we come together next time, we're going to take a deep dive into why these shapes are so important. Because if you draw this in any other way, you're actually drawing the incorrect molecule. If you make this look like a T instead of a Y, right, with one H coming directly up and one H coming directly this way, that is not correct. And it makes a big difference when we look at things like molecule polarity and bond polarity, which is what our discussion next time will be about. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.